Hello, I'm Yuqing Hu from University of California, Riverside. You might have heard AI ML accelerators like tensor cores and tensor processing units. These accelerators are now ubiquitous in computer systems, but with applications limited in just AI ML. Today, I'm going to show you our work, TCUDB, a relational database query engine that can use these tensor processors to achieve orders of magnitude speed up for SQL query that may not be AI/ML related. This work is done together with Yuliang Li from Megagang Labs and my advisor Hongwei Zhen from UC Riverside. Despite the limitation of processor technologies, both CPU and GPUs manufacturers are still managed to achieve 7 times to 9 times speed up in the past 8 years, as this graph shows. The graph shows the peak G-flops of different generation of CPUs and GPUs in the last 8 years. However, the demand of computation in applications, in particular AI and ML, grows even faster. It doubles every 3 to 4 months, far ahead of the improvement of general purpose hardware. To address the demand of AI ML applications, system designers and computer architects have found solutions to deliver orders of magnitude performance gain, as these bar charts show. The common magic behind these bar charts are AI ML accelerators, such as Tensor Processing Unit, Apple Neural Engines, Qualcomm Hexagon AI Engine, and NVIDIA Tensor Cores. Among these AI accelerators, Tensor Cores, or say TCUs, are by far the most easy to access and program. Therefore, this work mainly focuses on tensor cores. No matter which AI ML accelerators we used, they are essentially matrix processing units. Tensor cores that our paper exploits are specialized units that perform matrix multiply accumulate in one operation. For example, multiplying two 4x4 matrices involves 64 multiplications and 48 additions, while tensor cores perform MMA operation in just one GPU clock cycle. As matrix multiplication is an essential tool of linear algebra that powers the solutions for problems including data analytics, and database is the playground of these problems. We are interested in this fundamental research question. Can database application queries take advantage of AI/ML accelerators? In response to research question we developed TCUDB. In the rest of this talk, I will show you the opportunities we discovered for applying AI/ML accelerators like TCU in conventional relational DB queries. Then I will talk about the developed TCUDB and how we addressed the challenge of adopting AI/ML hardware in DB engine. Then I will show you the results with several case studies, and finally, I will conclude the talk. Now, I'm going to show you a motivating example that reveals the potential of AI/ML accelerators in DB queries. In this example, we have two database tables where table A contains the purchase log of customers and table B is a list of product and their manufacturers. If we want to figure out the contribution of each customer to each manufacturer, it is natural to compose the join query like this. With conventional DB engine, we will first create an intermediate table on the join key and scans table A to perform hash join in a pairwise vectorized manner to find the matching product ID. The final step for this query is to perform arithmetic aggregation and group by the result. However, the same query can actually be performed through a matrix multiplication. For table A, we can use each row to represent a customer and each column represent a product. We fill the purchased quantity from each customer as the value. We fill zeros for the rest positions. For table B, we can use each row for a product and each column as a manufacturer with the price as the value. The query result is indeed the matrix product of these two matrices. Remember, with AI ML accelerators like tensor cores, each matrix multiplication can simply be done with just one hardware operation. In other words, using AI ML accelerators can perform join aggregation with group by within one hardware operation. The aforementioned query is not the only case where matrix multiplication can apply. In section 3 of our paper, we list 4 categories of queries that matrix multiplication can produce the results and the algorithms of transforming these queries into matrix multiplication problems. Next, I will present a high-level overview of our proposed TCU-DB, followed by the challenges and how TCU-DB addresses those challenges. This is an overview of TCU-DB query engine. The query analyzer takes incoming SQL query, and then TCU-DB will pre-compute some metadata from input tables for the later use of query optimizer. The query optimizer will generate the corresponding query plan and driver code, which would invoke the certain TCU accelerated kernels to execute the query. You might think TCU-DB is just finding those patterns we mentioned and rewriting those queries into matrix multiplication. However, it is not as easy as you would imagine because we need to tackle a few other challenges. First, the tensor processor have a nature of low precision. For example, tensor cores is 16-bit. Second, naively apply MMA operation doesn't always guarantee the performance gain. The formulation of either dense or sparse matrices depends on the input data. Finally, all the hardware accelerators are restricted by the limited device memory. To address these challenges, I will next introduce the TCU-DB query optimizer, which is a core component in our work. When a SQL query comes in, the first step of query optimizer does is to match the query pattern. If not, the query optimizer will treat this query as normal CPU-GPU-based query plan. If the incoming query match our patterns, we then perform the step 2, the data range test. This is to avoid the case we got unwanted outcomes due to the loss of precision from TCUs. For those table inputs cannot pass the data range test, we will fall back to CPU-GPU-based plan as well. After pass the data range test, we will perform matrix density test using metadata pre-computed from input tables. If the density is smaller than our predefined threshold, we will perform sparse matrix multiplication during the execution. For the case that the density is greater or equals our predefined density, the optimizer will estimate the working set size to see if the resulting matrices are too large to fit in the GPU device memory. If that's the case, we will perform the block matrix multiplication to avoid out-of-memory issue. Finally, the optimizer estimates the query execution cost with TCU and compared with the estimated cost of CPU, GPU. The query cost estimator needs to consider the data transformation cost, which consists of computation and data movement overhead. If the original table size plus the working set size fits in the device memory, TCUDB can transform tables into matrix format within GPU to save the overhead of transforming data within CPU, as well as the data movement overhead. In the following slides, I will present 3 case studies of our evaluation. The first case resembles the motivating example we mentioned earlier in this talk. This query is join over aggregation, which is essentially a matrix multiplication. TCUDB shows up to 8 times speed up over YDB, a GPU engine on the same testbed with an NVIDIA Ampere GPU. This case shows that with TCUDB, relational database engines can potentially execute complicated arithmetic operation directly without other systems' help. Another case we studied is the blocking of entity matching problems. We use 2 real data sets from DeepMatcher benchmark. The left-hand side is the beer data sets, and the right-hand side is the music data set in this series of experiments. Compare against YDB, the GPU-based engine, TCUDB shows up to 288 times speed up. This case shows TCUDB's potential in handle complex data analytic problems. The last case we present in this talk is PageRank. In addition to YDB, we compare against both conventional CPU-DB engine, MonadDB, and MagicQ, a GraphDB engine. We use the Snap dataset and vary the graph size from 1K to 32K node. As the result shows, we achieve up to 4 times speed up over GPU-based DB engine using the largest dataset YDB can handle. Compared with MagicQ, our speed up ranges from 1.4 to 2.7 times. This result shows that with the help of AI ML accelerators, relational DB engines can be as efficient as GraphDB engines. The result should also encourage GraphDB engine to embrace the use of TCUs in their design. To conclude my talk, AI ML accelerators are ubiquitous. Database engine can take advantage of these AI ML accelerators even these queries are not AI ML related. TCUDB demonstrates a compelling use case, including matrix multiplication, entity matching, PageRank. We need to revisit application algorithms and data layout for emerging hardware accelerators. This work cannot be done without the NSF funding and the help from Megagon Labs. If you are interested in our work, you can visit our lab website, and we have our code release on GitHub. Thank you. I am ready to take your questions.